All right, welcome back to statistics this morning. So today we're going to start talking about confidence intervals when you don't know the standard deviation. Okay, so let me go ahead and share my screen with us. All right, and we are going to learn a new type of distribution today. Okay, so when you don't know the distribution, right, we can't say that it's going to be normal. Okay, we could say that it's close, but we can't say it's normal. Okay, so in comes the t-distribution. I'm not going to tell you what the formula is. It's a lot worse than the Gaussian. There's a whole bunch of stuff in there that's a lot of functions that you've never experienced before, like gamma functions and things. So we don't really need to go through that. Okay, but know that the shape of it is very much like the normal distribution. Okay, it's something like this. Okay, it's symmetric, so it's the same thing on both sides. Okay, but what we're doing is instead of, so here's the formula for the thing. It's x bar plus or minus, excuse me, there's a margin of error, right? It's the point estimate plus or minus. So point estimate is the mean, plus or minus a margin of error. And it's going to look very similar. Okay, so this is x bar plus or minus t, alpha over 2, same alpha as before. And then we have a degrees of freedom, and then s. So instead of using sigma, we're using the sample standard deviation over the square root of that. Okay, so s, remember, that's the sample standard deviation. And it's the sample size. This thing here, again, we have two things to look up to. We have a column and a row to work with. Okay, so again, these numbers, you're going to see numbers here. You're not to do anything with them. They are to tell you which column and which row we're looking up. Okay, now 21st century, this is a little old. I'll show you a t-distribution chart so we can see what's going on there. And this is the way we used to have to do it. But your calculator will do this information for you. But do not take these numbers and do anything with them, okay, except look them up on a chart. That's all they're for. So we could have a color and a shape, okay, for all we really care about, because they're not really numbers. They're just like, where do you look on the chart to get the number you want, okay? And they're going to tell you these things in the problem. Actually, the degrees of freedom, they're not going to tell us. Not explicitly. Okay, for us, for every problem you're going to do in this chapter, the degrees of freedom is always n-1. Okay, that's not always the degrees of freedom, but it is for this chapter. And the next time you're going to encounter this, which will be test of hypothesis in the next section, the next chapter rather. Okay, so that's our rule, is n-1. All right. Let me go ahead and show us a picture, a better picture of the t-distribution here. Let me pause this thing. All right, my mail up. I don't want to look at that. Okay, so this is what a t-distribution looks like. All right. We have another one. I don't. Hopefully, yay! Look at that. All right. So t-distribution, right? You can look at what's going on here. So if we have a small degrees of freedom, notice the little center part is larger, but the tail is bigger. There's more room for error in the tails. Okay, degrees of 10. Okay, it's the dotted line. So it's a little bit. The peak is a little bit higher. The tails are a little bit lower. Like, well, why does that have to be? Because the area is always 1. Okay, so when the degrees of freedom is infinite, it looks a lot like the normal distribution. Okay, so that's what we're doing with that one. All right, so it looks very much like the normal distribution, except there's more room in the tail. Okay, there's more room for the error for the red side. Okay, now one of the things we have to worry about is that t-distribution is really sensitive to outliers. Okay. So at the beginning of the class, we talked about outliers a little bit as cautioning you. People want to use a fancy technique, except there's outliers in it, so they throw out the outliers so they can use the fancy technique. This is the technique I'm talking about. Okay, it's a confidence interval, and if you have outliers, you can't use this technique because t-distribution is very sensitive to outliers. Okay, so what a lot of people do is they set them aside and then do the fancy technique and then put them back in. And sometimes that works out well, but it often doesn't work out well. So you want to be real careful about setting aside outliers, or at least make a note that you've done it, so the person reading your research will say, oh, there's an outlier. Okay, and there might be a good reason to set them aside. I mean, I can't measure it. Okay, maybe I can't do a rating. Okay, if you've ever made pancakes, or if you've ever watched somebody make pancakes, the first pancake, maybe the second pancake, it never comes out well. Okay, it's a little misshapen. The heat's not quite right, so it's either burned or underdone. But regardless, the first pancake is not a good pancake. Okay, so you could, and some things happen like that with machinery too. Like the first one of something you make, you turn the machine on and you start it, and whatever the first output is, it's generally not a good output. Either the machine's not done warming up, or it needs one to kind of get going, whatever it is. So if that's a reason for you, that we need to set this aside, this is not part of our sample group. Okay, nobody would ever include this in in rating us. So if you got to rate, like, let me see your pancake making skills. Like, you're not picking the first one. Okay, second one, the third one, sure, but not the first one. Okay. But a lot of times people just get outliers and they're like, that was inconvenient, let's get rid of it. Like, you can't, you need a reason to remove the outlier. You really do. All right. So t-distribution, very much like the normal distribution, very much like the z-distribution, except we have more room in the tail. Okay, that's what happens. And depending on what the degrees of freedom are, how much sample size you have, right, you might get something that looks closer to normal. Okay, so this would be like a degrees of freedom of like maybe 20, and then this one might be 5 degrees of freedom, would be 5. Okay, so the more degrees of freedom you have, the closer it looks like to a normal distribution. Obviously not drawn to scale. Okay, but that's the idea of what's going on. The area under the curve, regardless of the degrees of freedom, the area under the curve, it's a probability distribution. It's always 1. Okay, so we can kind of shrink it down a little bit, right? And then there'll be the tail will be compressed, or be a little bit lower, or we could squish it down this way. And then if we're going to do that, the tails are going to get a little bit bigger. Okay, so important to remember, the area is still 1. Okay, let me show you a table. This is what we used to have to do with this. Okay, let's see here. Do I have a table? I did make a table. So when we talk about this, okay, the confidence level, right, the t.9, okay, so this will be 95% confidence interval here, 97.5% confidence interval, 99% confidence interval. The little 99 part, okay, that's the alpha over 2. Well, technically this is the alpha over 2 here. And then we have our degrees of freedom. So I would have to tell you, hey, we're making a 95% confidence interval. That would be this level. And we have a sample size of 11, which means our degrees of freedom is 11 minus 1. Our degrees of freedom would be 10. So we'd have to come over here and get our confidence coefficient of 1.812. Why am I telling you this? The calculator is going to handle most of this anyway. And you're right, it is. If you have a TI-84, this is what you spent the extra money on right here, this is going to go a lot easier for you than people with a TI-83. Because the first question they're going to ask you is to generate some of these numbers. And I don't know why they do this, because like doing the inverse t-distribution to get these values, just like we had to do like an inverse normal distribution to get the confidence interval values. Normal distribution is a lot easier to calculate. T-distribution it's tricky, okay, to get the right one. So you can't just like inverse it. Well, you can if you have a T84. If you have a T83, there is no T inverse, okay? So if you have a T84, your life is not going to change. You're just going to select a different option, you're going to type in the numbers, and you're just going to go on with your life. T83, because that's what I have, your life is going to change a little bit. Okay. As such, I'm not asking you. I never ask this question. Okay, like this is a ridiculous question to ask. But you know, if I look at the first thing here, it's like find the critical value of A alpha over 2 needed to construct a confidence interval for a given sample size, around three decimal places. So we want 90% confident, 90% value here with a sample size of 8. So on a table, okay, the value we're going to look, they say 90%. Okay, so we're going to go T sub 90. Okay, and we're going to look at T90, and we have, what do they say, sample size? Did they say sample size or degrees of freedom? Sample size of 8. 8 minus 1 is 7. Okay, so I think what we're getting here, okay, is this 1.415. Okay, that's the one that they're going to want here. So let's go ahead and check 1.415. Okay, and so we're going to do that. Okay, otherwise, you have Excel. Okay, you have Microsoft 365, so you have this. Okay, and what you're going to do is you're going to type in t.inv. That's our t inverse. I have to go through the whole Excel thing here. Probability. Well, probability is going to be, okay, so we want 90% confidence interval. Okay, here's my 90%. How much is left over? Right, here's 90%. So 1 minus 0.90, that's going to be 0.1. And I've got to put this over in different pieces. So we have 0.05, 0.05. Okay, so my probability here is 0.05. Back to this one. So we have 0.05, comma, and you see degrees of freedom. So we have 8, right? We had 8 sample size, 8 minus 1 being 7. And I hope I get the same answer. Okay, I might not have read that chart correctly. I guess I didn't read it correctly. All right, so let's go back up here and go ahead and reconfirm this guy. Okay, so we have sample size of 7, and here we have 1.895. Okay, one tail 0.05. Okay, that should be my alpha, right? Alpha over 2. Alpha should be 0.1. Alpha over 2 should be a nickel, right? So we take a dime into a nickel. 1.895 to a certain amount of, 1.895. What did I say in Excel? 1.895. We don't care about, I don't know if you guys can see that. Okay, 0.05, 8 minus 1, 7 degrees of freedom, 1.895. Okay, so I'm gonna change my answer here. All right. And that's all they want us to do with this. I'm never going to ask you this question. Okay, so if you have a TI, when you do your distributions, a TI 84, you're going to see this T PDF. In here, you're going to see a T or an inverse T. Okay, TI 83 does not have that. Okay, so for you guys, it's going to be a little bit easier with the 84. You have the 83, you're going to have to go to Excel to do it. As such, I'm not going to ask you this question, okay? Because it's required for a lot of people. It's going to be required that you have Excel available to you, okay, or a chart. and you have to learn how to read the chart. So that's what we have. All right. Next point. Hold on. All right, there we go. Never understood the base thing. I think I'm old. Okay, so notice this one. We have a sample size n is equal to 57, mean, standard deviation. So the total is all the pieces we need. And we want to make a 99.8% confidence interval. Okay, so one thing about being 21st century, if I look at my table here, we have 57. 57 minus 1 would be 56. I don't have one. Okay, so on the table, we kind of had to make some adjustments. Okay, we had to get like our best guess. So that's one thing I could say, well, great, the 21st century, we don't have to do that anymore. Okay. So we have n is equal to 57. Okay. X bar is equal to 58.5. Sample standard deviation, S is equal to 9.5. And we want to know, like, what is a 99.8% confidence interval for this thing? We can go. Okay. So we're going to go to So we're going to go to stat. We're going to go to tests, and then we're going to go to T interval. Okay, we're going to do a T interval here. All right, and we're just going to type in the stats. We don't have any data to give it. We just have some descriptive statistics. I've got a mean, I've got a standard deviation, I've got a sample size. Okay, what was my point average? Right, my point average was 58.5. Standard deviation 9.5. Okay, sample standard deviation. Okay, and my n does 57. Okay, and then what kind of confidence interval do they want? You have to see a 99% on this. Okay, 99.8. Okay, so this is 0.998, and we're going to say calculate. Okay, I think T-distribution is not as easy as Z-distribution. Okay, so what's our interval here? 54.42. All right, up to 62.58. 62.58, 62.58. Okay, hopefully they only asked us to 2 decimal places. 1 decimal place. Okay, I could live with that. So what do we have? We have 54.2, 54.4 rather, to, we'll say that's 62.8 or 60.2, 62.6 rather, 62.6. Okay, that's a terrible 6. All right, so we're going to go from 54 point, what are we doing here? 54.4, and then 62.6. Right. So that's the mechanics of calculating it. Okay, there's dozens of problems that we could do for that. All right. Now, they just want to know. Okay, let's do an experiment. If the sample size were n is equal to 54, would the confidence interval be narrower or wider? Okay. So instead of 57, we're going to say 54. It's not that big of a deal. If you want to recalculate it, I suggest you do, but let's think about it for a minute before we go off and do it. Okay. So if I go from 54 to 57, okay, again, not drawn to scale. Easier with different colors. Okay. This is a little bit more spread out. Okay, the blue one is a little bit more spread out. There's more room in the tail. It's a little bit more spread out. Okay, so we're going to look at that. We're going to get confidence coefficient is going to be a little bit smaller, or actually, sorry, a little bit larger. Okay, the red one, they're going to be a little bit smaller. Okay, so if we lower the sample size, right, we're allowing in more uncertainty. Okay, and we got to account for that. So we're going to be right a little bit. The confidence interval is going to be a little bit larger if we have that. You can, you know, if you looked up one of the things here, right? Look at the values for like low levels of confidence, right, or low levels of degrees of freedom rather. So if we just pick, you know, T95, look at this, like 2.353 for low ones. Okay, 2.015, and look what happens to them as we go bigger and bigger and bigger here. Okay, to where we get to Z. This is how we used to have to do 8.1 too, by the way. Let's look at this column. Okay, but these are much smaller numbers, so the confidence interval is not as big. I'm multiplying by a smaller number. So confidence intervals for low degrees of freedom, right, are a little wider than not. But you know, you're new at this, and we're learning it. And if you say, you know what, I'm not gonna, you know, I don't trust myself yet, that's fine. Okay, we can go over here and say tests. Okay, type in T interval instead. Okay, and instead keep everything the same, but we're going to go 54 instead of 57, and let's see what happens. All right. So there's no reason why we can't do the experiment. All right, what do we get? We got 54.3 to 62.7. 54.3 to 62.7. So it got a little, it wasn't much, but it got a little bigger. Okay, so the interval was going to be a little wider. Okay, and then we're going to be okay with that. Okay, so I would encourage you, like, try to train your intuition a little bit, but don't stress over it, because recalculating it took us all of what, like 30 seconds, and most of that was waiting for the calculator to come back with an answer. All right, so don't stress over that. That's the way to check. Okay, this is why I tend not to ask this question, because I can't be sure if I'm testing your intuition or I'm testing your ability to punch in 54 rather than 57 into a calculator. So I generally don't ask, but it is good to get an idea of like what's going to happen. Okay, because quite honestly, you're always going to be calculating these things with a calculator. Okay, we don't, yeah, but the idea of like, well, what if this changed? You know, would you be able to think the way through the answer of what if this changed? Okay, and that's all we're asking you to do. Okay, so a sample of 256 college students, or 256 students were taking an online class were asked to describe their overall impression of online learning on a scale from 1 to 7, 7 being most favorable. Average score was 5.25 and standard deviation was 0.85. Construct 80% confidence interval for the average score. Okay, so let's go ahead and take a look at what that's going to look like. All right. So what's our sample size, right? Our sample size was, we had 256, was it? 256. Okay. And their average score was a 5.25. So X bar, right, is 5.25. Our standard deviation was 0.85. So our S, 0.85. Okay. Our N is bigger than 30, so we could say that, you know, it's going to be approximately normal, but since we don't have sigma given, right, we have that little bit more uncertainty because we're using our statistic rather than a parameter. Okay, there's a little bit more uncertainty here. We've got to use T. Most of you, if you do this for a living, most of this is going to be T. Okay, I don't know why they teach us Z to kind of ease us into the idea. Okay, but in practical things, you're never ever going to use Z. Okay, we're just never afforded like that much certainty about anything. So finding 80% for the confidence interval. Okay, so there we go. I'll tell you why Z was important. It's like, remember that chart I showed you? This one? There's no 256 on here. And some of your sample sizes get to be like over 1,000. And at that point, they just say, you know what, use Z, because that's the approximation. But we don't have to do that because we have a calculator. It'll take care of the entire thing for us. Okay, so here's our values. Okay, let's make a confidence interval. So we're going to go back to our calculator. Okay, and again, they just gave us descriptive statistics. They didn't give us 256. Thankfully, they did not give us 256 numbers that we would have to kind of sort through. Okay, so we're not going to do that. We're just going to say stat. We're going to say test. We're going to go down to where it says T interval. Okay, and then we're going to type in our data. Right, we have stats. We're going to say, okay, great. What's our average? It is 5.25. Okay, our standard deviation was 0.85. Okay, our N 256. Okay, confidence interval. They wanted an 80% confidence interval. That's going to take a bit. Oh, actually not good. Okay, we got a 5.18 to a 5.31, 5.32 rather. So the true average rating, okay, the mu, we have an 80% chance, it's not very high, an 80% chance that this mu is inside of this confidence interval. Now, this can float because depending on the sample we got, and depending on the sample and the standard deviation, this can change. Okay, these two values can change. This is a constant. This is never changing. Okay, whatever the parameter is for the average, like that's constant. But our confidence interval, that can float around. That could be variable. Okay, so confidence interval here is going to be 5.18, 3.5. Come on. 18 to 5.32. That was it. It was. Okay, so we're good. Check our answer. Fantastic. Okay, now part B. Assume the mean score for the students is 5.48. Okay. College that offers online classes claims that the mean score for their online classes and traditional courses, is traditional courses is 5.48. But for online classes, it was a little different. And they're saying, no, they're the same. They're going to work out just fine. 5.48 is not in my interval here. Okay. So if you're going to say that you think they're the same, like honestly, you're going to have to come at me with a little bit of evidence to support your claim. Because 5.48, this is outside of my interval. So if you're going to tell me that they're the same, you have to show me some evidence that that is the case. Okay. So that's, I mean, I guess you could, instead of an 80% confidence interval, you could have used like a 99.9% confidence interval. That's going to make this wider, and then it might include. Okay. But right now, with what we have, okay, we can't say that that's true because our confidence interval does not include the 5.48. Okay, so the confidence interval does contradict our belief. Okay, that's what we're using this for. All right, let's see here. All right, so just score. This is kind of the same problem that we just did. That's okay. Okay. We asked 846 adults. So my N is 846. What's my degrees of freedom? Is 845. Okay. So 845 degrees of freedom. Don't have that on my chart. Okay. The average was 8.34. So my my X bar, right, that is 8.34. Okay. And the standard deviation was 8.15 years. So standard deviation, oops, not that. This is 8.15. You think this is a symmetric distribution? Right? Is it possible somebody could have like -1 standard deviations, right? They left in the first grade, okay, halfway through it, a quarter of the way through first grade. I mean, it's possible. 2 standard deviations, like, no, you can't have negative. Sometimes you talk to people, you think they've had negative years of education, but that is an impossible thing. All right, construct 99.8% confidence interval, and then we'll figure that out. Okay, 2 decimal places. So here we go. So stat, tests, okay, t interval. Okay, we're going to input some values here. So we're not going to need data. We didn't get numbers for 846 people. Okay, just have this. So what do we have here? We have 8.34. That was my average. 8.34. Okay. My standard deviation was 8.15. Okay. Total number of people asked, 846. Notice we don't use degrees of freedom here. We're just doing sample size. The calculator can subtract 1 just fine. Okay, and we want what kind of confidence interval? 99.8. 99.8. All right, and calculate. That'll be a while. All right, so our confidence interval is showing, okay, my confidence interval is showing that we have about 7.47 to 9.2, call that 9.21 years of education. Okay, so that's the true average. So that's our true average. I would have thought of it closer to 12, but all right. Guess a lot of people they asked like dropped out of school in like the 6th grade or something, but whatever. Okay, people can get along. So what do we have? We have 7.47 to a 9.21. Okay, that's the average number of years of education. I keep trying to make sure that I didn't miss something ridiculous, like how many years of education he had past primary school or something. But no, that's the answers we got. That's the scenario we have. So check. All right. Data collected in an earlier study suggested the mean was 6.93. Sociologists believe the mean in 2012 would be the same. Okay. Does the confidence interval contradict this claim? So yeah, this is a pretty wide confidence interval, right? From 9.8%. So clearly it's gone up, right? The amount of education we've had is gone up from 2000 to 2012. Okay. So because the 6.93 is outside of my interval, I'm like, could you bring your study? You know, could you cite something? Let me know. All right. So the confidence interval does contradict the belief. Okay. So there we go. I think this is going to be the same problem that we had previously. So we're going to go ahead and skip that one. I think you're probably getting to the point now where maybe these are getting a little bit easier to kind of deal with that. All right. Okay. So phonics is an instructional method in which children are taught to connect sounds with letters or groups of letters. Okay. We have a sample of 131 first graders who are learning English. we're asked to identify as many letter sounds as possible in the period of 1 minute. Okay, the average number of letter sounds identified was 34.11, standard deviation 23.91. Okay, so we're going to construct 99% confidence interval for this, for the mean, right? Because we're looking for the average, right? We're going to have like people that are not going to fall outside of this, but that's an individual. We're looking at a group, okay? So we're going to round answers to decimal places. Okay, so what do we have? We have sample, so that's n is equal to 131. Just in case anybody ever asked, we have 130 degrees of freedom, okay? And the experiment was to ask these first graders, please identify as many letter sounds as you can, and we're going to time you, okay? No pressure. Okay, so the average was 34.11, okay, and standard deviation S, because it's for the sample, okay, the average number of letter sounds, the sample, 23.91, okay. How do I know it's you know, you have to be able to read this and kind of determine, because this is what you're going to be doing. It's like, well, is it an 8.1 problem or is it 8.2 problem? I don't know. As we go through and read this thing, a sample of 131 first graders was learning how to speak English. They were asked to identify the letter sounds. The average number, and the average number of what? The average number from the sample, okay, is referring back to the sentence previous to this. The average number of the sample of letter sounds was 34.11 with, this is the same sentence, right? Second idea in the same sentence, compound sentence. It's again referring back to the previous one with a standard deviation, a sample standard deviation, 23.91. We now do a compare and contrast. Look back at one of the problems from 8.1 and notice how they tell you what the standard deviation was. They'll say something like the population standard deviation was sigma equals. Okay, so it's really important. Compare your 8.1 problem to your 8.2 problem. Why are they similar? Why are they different? Okay, it's going to go a long way when you're on a quiz. It's like, well, which one do I pick? I don't know. You have to read it. Okay, so if they tell you it's a sample standard deviation, or they imply it's a sample standard deviation, sorry, English literally is truly a poor language for this. You have to use the sample one. You have to use T. If they gave you the population standard deviation, then you use Z. Okay, there is a difference. You type in the wrong one, they're going to know. Okay, I'm going to know. I'm going to look at what you wrote and say, look at that. They screwed this up. Okay, it's a minus. Okay, so it's not like the whole problem is wrong. Okay. All right, and they want 99.5%. 99.5% confidence interval. All right, so we plug this in. Okay, so we're going to go to stat, tests, down to T interval, and we're going to use that. Okay, so where we have stats, we have a bunch of descriptive statistics. So our average was 34.11. Our standard deviation, right, that was 23.91. Okay, still probably not empirical roll. Okay, I don't think it's bell-shaped or anything like that. 131 sample size. Okay, and then my confidence level was 99.995. Okay, don't forget to change this into a decimal. That's how you have to do it. All right, thinking a little bit. Okay, so we got 20.144. 28.144. What am I doing? 28.144. Okay, to 40.076. So 40.076. Okay, we have a 99.5% chance of covering the. Look how wide that is. Okay, we have a 99.5% of covering whatever the true mean, right? Whatever the actual average is that first graders can identify for sounds. Like, what is that average number? we have a 99.5% chance of saying it's somewhere within here. But still, 5 times out of 1,000, it's going to be somewhere else. Okay, the answer might actually be 52, right, for the true mean. And this will be the one sample that we got that didn't fit. Okay, it's unlikely, but it is possible. Okay, so if somebody comes by and says, well, I think our phonics program is doing better, we got 45. That was our average. Like, did you bring your test results? Did you bring some numbers? Did you bring anything? If you didn't, then I can't believe you. I don't have evidence to say that that's true. However, you say, we're doing, we think our phonics program is really well. We got an average of 38. Like, okay, I can believe that. That seems like somewhere within the average that we found. Okay, I wouldn't say it's significantly different than what we have, right? I can't notice a difference. That's why I use the word significant. It's like we are trying to notice a difference, and I can't. Okay, I don't know if you guys ever, I don't know. I'm trying to think if that's an appropriate fairy tale to still tell. I think it is. So I'm not sure. What do we have here? 144. Is that what it was? 144, 40.076. 40.076. Okay. So there's a fairy tale that goes along with the princess is visiting something, or they're trying to figure out if she's actually a real princess. And they stack a bunch of mattresses up, and they put one pea. I think it's uncooked. One pea at the bottom of all those mattresses. So the real princess would have to sleep on a pristine bed. Okay. Will she notice the pea? That's what we're all playing here. Is like, can we notice that pea that's under all these mattresses? Okay. So all the difficulty. Okay. Maybe that is a little sexist. Okay. So we have, if a 99.9% level confidence interval were constructed with these data, would it be wider or narrower? Well, the more confidence you have, the bigger target you have. Okay. So it would necessarily be a wider interval. Okay. So this should be a wider interval. Remember, 100% confidence, we can't have that. It's too big. Like at 100%, you can say, well, it's a number, right? Somewhere between negative infinity and positive infinity. All right. So it's going to be a little wider, okay, than what we had calculated. Although, way to go, guys. Run the gamut from A to A point B or something. It's like, it's not very big. Okay. We've run the gamut from A to A. All right. Give me something I can notice, like, 80% to 99%. That I can see. Okay, the following weights in pounds of 2-month-old baby girls. Is it reasonable to assume that the population is approximately normal? Same problem we had in the last section. Okay, there is a tool to do this. We don't teach it anymore. The book doesn't cover it anymore. It's out of our student learning outcomes. So we don't do this. Okay. So I'm going to say sure. Okay. If they could say, no, that's not correct, like I'm going to have to just deal with it. Oh, is it? Okay, they're asking, is it reasonable to assume? Okay, you don't have a tool to do this. All you can do is stare at the dot plot and say, sure. Okay, so I never ask you a question that looks like this because I don't want to rely on your expertise at this point to say if it is or isn't. Okay, I don't want to rely on mine either, because a lot of times I look at it and say, I don't think so. And they say, yeah, it is. Okay, there's a test. Okay, just like all the tests that we're doing right here, there's a test to see if it's normal. So we say, okay, construct a 90% confidence for the mean weight of 2-month-old baby girls. All right, so what we're going to do is that we are going to, I want to go on, I want to go to stat, tests, and we're going to go to T interval. Now, in this case, they gave me some numbers, okay? So I don't, they're going to give me numbers. I'm going to have to put them somewhere, aren't I? So let's go ahead and quit out of this. Go back to stat. I'm going to clear. Oops. I'm going to go ahead and say clear list 1. All right. Clear list 1. So now I have a place to put these numbers. So we're going to edit the list. Okay. And we're just going to type these in. 12.32, 8.51, 8.51. What am I thinking? 8.51. Okay, 11.87, 14.13, 12.34, 12.95, 11.48, 9.34, 12.66, 8.63. Okay, there we go. We have 10 2-month baby girls there. All right, stat, tests. Okay, we're going to scroll down to where it says T interval. All right, and then instead of stats, we're going to say data. Okay, so we're just going to input the data, and notice most of those options went away because I don't know what the mean is until I calculated it. But I've already gave the calculator the data; it can calculate it. So it's there on list 1. Frequency, we're not going to worry about that because we're not getting that fancy about it. So it's 1. Confidence interval, what do they want? They want 0.90. And then calculate. This is like my favorite flavor of T confidence intervals, by the way. So as the calculator's going, just realize, like, if I'm going to come up with a, I'm going to come up with a quiz question on this section, it's going to look a lot like this. All right, so a small number of numbers to give you, so you don't have to type everything in. Right, you're not going to be spending 20 minutes typing this in, and you get the thing right here. It's S. So when it says S, you have a T distribution. You have sigma, you have Z. But S, you're going to have T. So it tells you. Okay? Confidence interval for 2-month baby girls. 10.3. What do they want? 3 decimal places. My goodness, our calculator gave us that. So 10.302. Okay. And the upper one is 12.544. Okay. Alligator's mouth eats the bigger one, so the numbers always go from low to high. Okay. All right. And let's see. They give us some information about baby boys. So they said 13.9. Is 13.9 in my interval? No, it is not. So it is not reasonable to believe that the mean weight of 2-month-old baby girls is the same as 2-month-old baby boys, because their average weight is not inside this interval. If it was, we'd say sure, it's reasonable. But there we go. All right, this would be like the kind of thing to pick for a quiz question. Okay, so if you study when you study for your quiz for this, a problem like this is exactly the kind of thing I would pick. Okay. Same thing with this one. Okay, same thing. And I won't ask, is it reasonable to assume the population is approximately normal? This will be a declarative statement instead of a question. It is reasonable. Assume it is reasonable to say that the population is approximately normal. Okay, because we're still kind of relying on that CLT thing. Okay, if it's not approximately normal, we got to pick a different confidence interval. Okay, and our class doesn't, the whole class doesn't even go into that. So we're not going to do it. Should we do this one? Sure, let's do this one. Edit. Oops, I want to say stat. Clear my list. So enter. Clear list number 1. There we go. And we are going to edit and enter in a whole new thing. So what do we have here? We have 14 boxes of cereal. Okay, so we're going to have 13.99. Okay, 13.96. 13.96, 14.02, 14.08, 14.01, 14.0, 9. Let's get rid of that part. We have a delete button. Okay, another 14.08. 14.07. No. We're going to get used to this laptop. 14.09. 13.99. 14.02. 14.12. And 14.01. Okay, do we have 14 things? Yeah, well, let's get down to 14. Okay, let's just double check real quick. Okay, so 13.99, 96, 96, 02, 08, 01, 09, 08, 07, 09, 99, 02, 12, and 01. Okay. So stat, tests, T interval, enter. We're going to give it the data. The data is going to be in list 1. I didn't worry about a frequency. What confidence interval do we want? Well, confidence interval we want is 90%. Oh, look at that. We're already done. All right. And I'll just say calculate. It's going to take a little bit. All right. There we go. So 14.01 to 14.06. Okay. So by the way, if you're in quality control, this is exactly the calculation that you're going to be dealing with. Okay. You're going to have a set confidence interval. You would have had meetings about this. Okay. Oh, they want 3 decimal places. What am I supposed to do? We'll put it in there and hope for the best. Okay. Really? We only got, yeah, we only got 2. Okay. We're hoping for the best here. But you want to make sure that your confidence interval is a little bit over the advertised price, the advertised amount, because if it isn't, you can get sued for, not for false advertising. And as a quality control person, like that's one of the big things you want to make sure of is you're not being sued for something like that. Okay, they're going to get upset. Oh, I guess they were just kidding when they said 3. Okay. So this is exactly the question. It's like the quality control manager is concerned that the mean weight is actually less than 14 ounces. Based on your confidence interval, should you be concerned? No. You should not be concerned. The mean weight is actually, should not be concerned that the mean weight is actually less than 14 because he's worried that we're going to get sued. Okay. It's like, nope, look, we have a confidence interval. We can show it. If somebody takes us to court, we can say, hopefully you'd have a little bit more data. Okay. And then here's what the defense lawyer would say, or the prosecutor rather. Why did you choose a 90% confidence interval? Because if I choose a 95, this will be a little wider and it might include things that are less than 14. Okay. So you'd have to be able to say we chose 90% because, and again, there'd be a whole, like, that's not a one-person decision. Okay. This is we're gonna, if it was a one-person decision, I'd throw a dart, I'd say, okay, 95 is it, because that's the standard. Okay. Well, whatever we have here, whatever reasons they pick this, that's what you would say. Okay. And as long as they were reasonable, I think you're gonna, that court case would be just fine. Right? Unless you were truly shorting people, then this wouldn't show it. Okay. So here's, okay, this is a good question. Because random sample with 9 college freshmen were asked how many hours of sleep they typically get per night. Okay, the results were, and they give some reasonable ones, except this one, right? Nobody sleeps 24 hours, right? That's not happening. So when you see that, you're like, oh, look, we said somebody who slept 24 hours. I know that technically it's an outlier, but unless, I probably wouldn't worry about it, or I wouldn't bother, knowing that, people that are 18, 19 years old are prone to exaggeration because it's funny. Okay. So yeah, I would just toss this one out because clearly this person didn't answer honestly. Okay, I would throw this one out. So in this case, the throwing out the outlier is a correct choice. Okay, so the data contains an outlier, clearly made a mistake, or make it a joke, whatever. Eliminate the outlier, then construct an 80% confidence interval for the mean of absolute for the remaining values. Okay, that's all we're doing. So that's why it's a good problem, is because it gives you a practical application of a result you might actually see, and it would be up to you to say, I don't think this is true. Okay. You're not in college and sleeping 24 hours a day. Okay. So if we wanted to go through this, again, we're going to go to stat. We're going to go to clear list. Okay, second function there, boom, there, and then we can go ahead and list these things in here. Okay, so what do we have? We have 8.5, 9, 20. Well, we're not going to put the 24 in. We have 8, 6.5, 6, 9.5, 7.5, 7.5. Okay, we have 8 remaining observations here, right? We have 9, we tossed 1 out, we have 8 left. Okay, so what we're going to do is we're going to go to stat, we're going to go to tests, we're going to go down to where it says T interval. I'm sorry this video is long, but I looked at the time and I said, we only have so many more to go, so we'll do it. Okay, and the data, it's list 1, frequency, we didn't mess with that. We're going to do with 0.8 for an 80% confidence level. And then we're going to say calculate. It's not going to take as long. Okay, maybe I lied. But there's our interval. There's our average standard deviation. Degrees of freedom, 7. 8 minus 1. Okay. So we would write down, what would we write down here? Write down 2, how many? See, now I got all the decimal places in the world. What do they want? 2 decimal places. 5.22 or 7.22, rather, 7.22, 7.22, and 8.41. Okay. Check. All right, they're happy. Leave the outlier in and construct a 90% constant. You got to, we want to do the whole thing. Actually, the thing is with this is it doesn't matter which order you put them in. Okay. Oops. Dang it. One more. 24. Okay. Now we'll do the same thing. Okay. Test. All right. T interval. Say everything is the same, right? 80%, everything is the same. Okay. Now look what we get. We get 7 to 12. Okay, because we put that one outlier in. Like, look how much it skewed it. Okay. So this is going to be still how many 2 decimal places? So 7.05, 7.05 to, what are we doing? 12.18. Okay. Are the results noticeably different? Yeah, I think we can tell the difference. Okay. So yes, the results are noticeably different. The results. Why did they not ask us any questions for following up? Yes, they are. Okay. In college, you get a yes or no answer. The answer is yes, because, and then you make your case. Okay. So let me make my case. Outlier. Distort. Confidence interval. 1 T-distribution is sensitive to outliers. And 2, standard deviation is wider than it should be. Right? If we're going to include that outlier, the spread is going to be more. So it's kind of messing it up on 2 things. The T distribution, it is sensitive to outliers, and then we have it's a, you know, the standard deviation also gets to be bigger than it really ought to be. Okay, so there. I wouldn't ask you for like an in-depth discussion about this, by the way. Yeah, that's too much. Okay, but I also wouldn't ask you this question either, because like, yes, I don't want to teach you anything where you can say yes or no question. Yes, be done. Because what do I know? I mean, you know, flip a coin. Like, oh, yes, there you go. We're done. All right. Enough of me talking. Go do your homework. Okay, follow along here. Calculator is going to be your friend. Note, I will never ask you a problem like number one. So if you get through it because you have a T inverse button, go ahead and do that. If you don't, do the best you can with the charts and Excel, but I would not waste, like if you end up getting like a 9 out of 10 on this homework, I would not waste more time trying to figure out number one. Okay, I just wouldn't do it. So we're gonna call it in there. Okay, and here we go. Okay.